Hi everybody, Professor Burns here, and we are taking a look at Laplace transforms. So this is our third unit in the course, and we're going to use Laplace transforms to help us solve initial value problems. Of course, that's the point of most of these techniques, is learning how to solve these equations. And so as we go through this chapter, we'll see more and more how these are applied. So to start off, though, we just kind of want to get into what does a Laplace transform look like? And how do we kind of work with it? We want to get used to working with it. So make sure you have your notes packet in front of you, your cell phone is put away, and you're ready to go for the next few minutes. So first of all, what is the Laplace transform and how does it work? Well, if we have a function, I'm just going to call that function for now f of t, and we know that that function exists for any values that are 0 or bigger. Then the Laplace transform for that function, if it's lowercase f, they're calling it capital F, although that's not as important later on, is defined by this integral. So let me write this down for you. F of s. So f of s is going to be the function, and it's going to be defined as the integral from 0 to infinity. So it's an improper integral of e to the negative st times f of t with respect to t. So whatever that f of t function was to begin with. So we're going to evaluate this improper integral from 0 to infinity. The domain for f of s is all values for s over which the interval exists. And we may write this as capital F of s, but more commonly, and this is kind of maybe how I learned it, I write it using this sort of script L for Laplace of f. So that would be the Laplace transformation for the function f. So let's do a couple examples here where we actually practice computing this. So the first one says, find the Laplace transform for the function f of t equals 1. So we're just looking at the constant function 1. And I'm going to go ahead and just set it up using the definition. So f of s, we'll use the capital F for right now. It's going to be the integral from 0 to infinity. So we've got the integral of e to the negative st, and then f of x, or f of t rather, is just 1. So remember how to do an improper integral from Calc 2. I always write this as a limit. So I say the limit, and I use b for some reason, no particular reason. I just say the limit as b goes to infinity of the integral from 0 to b of e to the negative st dt. And we're going to treat s as a constant, basically, and t is the variable that we're integrating with respect to. So if s is a constant, then the integral of e to the negative st, think about if you did a little kind of a mini u substitution, you would end up with negative 1 over s e to the negative st. And remember, we're doing the limit as b goes to infinity of that integral evaluated from 0 to b. So that's going to be negative 1 over s. Remember, s is a constant. E to the negative s times b minus negative 1 over s e to the, it would be s, negative s times 0. Of course, we know that's going to just turn into 1 in just a minute. And we're taking the limit as b goes to infinity, so I'm going to sneak that back in there. All right, so think about what happens. I've got negative sb, I've got a negative exponent, and b is growing, b is going to infinity. This moves to the denominator, of course, because of the negative exponent. So if I've got 1 over larger and larger values, and I take the limit, that's going to 0 out. So I end up with just positive 1 over s, because remember, this is just going to be 1. And that's it. So that is the Laplace transform for function, just constant function of 1. All right, let's do another example here. Determine the Laplace transform. So this is that other notation. It's like a sort of script L of sine of b of t, where b is our constant. All right, so we're going to set it up using the integral definition. So f of s is equal to the integral from 0 to infinity of e to the negative st times sine of bt with respect to t. So I'm going to write this using a limit. Now, since there's already a b in the function, I'm going to use a different variable here. I'm going to call it the limit as c approaches infinity of the integral from 0 to c of e to the negative st. So s is going to be treated like a constant times the sine of b. B is treated like a constant, of course, bt with respect to t. So my variable is t here. Now to integrate this would require integration by parts. This is a cyclic integration by parts problem. I am not going to make you trudge through all of the details with me. I'm just going to get right to it. But if you want to pause the video, and I encourage you to do this, maybe on a separate sheet of paper, go ahead and do the integration here using, I love the tabular method even when it's cyclic, but you don't have to use that. It is integration by parts though. And then start the video back up with me. And what you should wind up with, let me go ahead and just give you the antiderivative here. So let's write this out. I've got the limit as c approaches infinity of b squared over b squared plus s squared times negative e to the st over, e to the, st over b, sorry, I'm looking at my notes here, times the cosine of bt plus s over b times the sine of bt. And we're going from 0 to c. All right, so let's replace it with our limits of integration. So we've got the limit again as c approaches infinity of b squared over b squared plus s squared times negative e, oh, you know what, I'm sorry, I missed a negative sign here. Make sure you fill that in. That's very, very important. You'll see why in a second. Negative s times c over b times the cosine of bc. Sorry, there's a lot of variables here. S over b times the sine of bc, and then all of that minus, let's come down here and write it, negative e to the 0 power over b times the cosine of 0 plus the s over b times the sine of 0. All right, so bear with me here. I know this is pretty hideous looking, but let's just kind of think through what's going to happen here. So as c approaches infinity, this negative exponent, remember that's why I said this negative is important. Make sure you have that. That's going to move that to the denominator, and c is going to get larger and larger. And that's all getting multiplied by this cosine plus the sine term here. So as c gets larger and larger in the denominator, this entire expression here is going to zero out. So that's where that limit is going to approach. As far as the rest of it goes, we've got e to the 0 power, well, that's going to approach 1, and it's negative, but there's already a negative here, so it actually is going to be positive. 1 over b times the cosine of 0, which is 1, of course, and then sine of 0, which is 0. So that gives me, remember this b squared over b squared plus s squared was in the front. So we have b squared over b squared plus s squared times basically what was left. Remember, you had a negative and a negative, 1 over b. And that's really what that limit simplifies down to. And I've got a b squared over a b, so that reduces and leaves me with b over b squared plus s squared. And that is the Laplace transform for the sine of bt function. So in this first section, we're just going to kind of work through some of these. We're not going to get too crazy with these, but we're going to work through some of these using this definition to actually find the Laplace transform. And as we get further into the chapter, we won't do this every single time. We're going to have some charts and some tables we'll use with some common Laplace transforms, including the ones we just saw, and we'll start referring back to those instead of using this every single time. But for now, in this first section, we're just going to practice applying this definition and evaluating these improper integrals. So make sure you bring your notes to class, and I'll see you tomorrow.